So you do it just like I would do like number 2. So I'm going to rewrite my n factorial. That's going to be n times 1 less than n, right? Which is, I would write that like that. And times this guy, and so on and so forth, but I can actually just do that. And then we can do that guy right there. Next one, I'm going to start with my n minus r plus 1 times n minus r plus 1 minus 1, right? Which is just that guy, factorial, which is just this guy, factorial. So we end up with m. So these are the scenarios that you come up with. They usually love them on standardized tests, speaking of. It's a multi-event process where there are m possible outcomes for the first event. They use m base 2, so m of 2, m3, m4, all the way to the total possible outcomes. And then you get this spider-like thing that happens because, like, for example, right here, they have a tree diagram. It says there are several options for fall and spring sports. If the playing a particular fall sport does not affect the playing of another particular sport, those sports are independent. And so they give this diagram of soccer, cross country, and volleyball. So this is where we have our first row. And then they want to see what happens if we have baseball, track, in the spring sports, and then all the possibilities. And so you start with, well, here we could have soccer, and they could either do baseball and track from here, or cross country, baseball and track, or volleyball, baseball and track. And so you see how we come up with all of these possibilities. All right. And so this is great when you have 2 options, right? But then when we start throwing in like 4, 5, 6, I don't want to draw a tree. Actually, I never do this. I always do the counting principle. And so, but this is where the basic counting principle comes from, is that you have all your options here. They're independent of the options that happen here, and so on and so forth. And so you end up doing a multiplication process. And so if you look at this one here, they drew this nice little tree for us. A school fundraiser poster claims to offer 12 meal combinations. Participants can choose a fried chicken plate or a spaghetti plate as the main course, a dessert of chocolate cake, banana pudding, or pecan pie, and either tea, coffee to drink. All right, so they've given us the little tree here. And they're saying, hey, what happens here when we do this? Really, the easiest thing to do is just to multiply. So we actually have 3 choices. And so we're going to look at those 3 choices. First, are they independent? Yes. It does not matter if I choose chicken or spaghetti. It does not affect my choices for dessert. That's what they're talking about when they're saying is it independent. All right. And so all I'm going to do is I'm going to say, well, I have a main course, right? Main course, I have dessert, and then I have a drink option. Those are really my options. And I'm going to put all the possibilities in there. I have 2 possibilities for my main course. I have 3 possibilities for my dessert, and I have 2 possibilities for my drink. And then you just multiply them. Right? That's the counting principle. Much easier than drawing a tree, by the way, just so you know. All right. And so if they're independent and one doesn't affect the other, you're really just multiplying your options to see how many options you end up with. There's 12 possible combinations of plates that could be made from all of these. All right. And so no one's ever going to ask you to list them, but they will ask you how many options there are. Right. And so that's your option. It says a local deli offers triple scoop ice cream cones. For each case, find the number of different arrangements or distinct orders of flavors and whether they are independent or dependent. The first one, the deli has 5 flavors and the cone can contain repeated flavors. Are those independent or dependent on each other? Independent. They're independent. If it doesn't matter if you repeat, then it doesn't matter what you do the first time, which means I have a triple scoop, so triple meaning 3. So for A, my first options, I have 5 options there. My second scoop, I have 5 options, and my third scoop, I have 5 options. There are 125 different possible ice cream cone combinations. You wouldn't think there would be that many, but there are, from just 5 flavors. Look at the next one. The deli has 5 flavors and the cone cannot contain repeated flavors. Are these dependent or independent on each other? They're dependent. What I make my choice for the first one affects the fact that I no longer have 5 options for my second one. I now have 4, and then this guy only has that many. And so then we drop to 60. It drastically changes, by the way. Repeating matters. There are 28 choices, and it cannot contain repeated. Dependent or independent? Dependent. And by the way, many, many more options. 30 wonderful flavors then would be lots of options. There we go. All right. That's just your basic counting principle. Look at 3. A computer programming team consists of 8 members. How many ways can they line up for a yearbook photo? Is this dependent or independent? Dependent. Yeah, because guess what? If Michael is in the first picture, first line, I can't repeat Michael, right? So these are dependent on each other. And so if we look at 8 members, then how many spots am I going to have when I line them up? 8. And it's going to end up looking like this. What does this actually look like to you?
8 exclamation mark.
There we go. Hence that little guy right there. Factorial, okay? And so very often when you use up all of the options and you go and they're dependent, you end up doing factorial. That's what ends up happening. How many ways can president, vice president, and secretary be selected? Dependent or independent? Yeah, you can't have the guy that's president and vice president. That doesn't usually bode well. So, but for the first spot for president, how many options do I have? 8. For vice president, I now only have 7. And for secretary, I only have 6. This is not going to be factorial because we don't use all options. We're only using 3 of them.
Could that also be like 8 factorial minus?
Order is important is the first thing you want to remember. Permutation, you can do this in your calculator. There's a permutation key when you go into your math and then your probability menu. But the actual formula isn't that bad either. It's the number. So that first n, when you're talking about order, is all of your objects. So if we have 13 people in the class and I want to pick president, vice president, and secretary of PreCal, right? N would be the number of people I have to choose from originally, all right? That would be all of my objects. And then the second number tells me how many I'm taking, all right? So if I'm saying secretary, or president, vice president, secretary, that's 3. So I'm taking 13 people 3 at a time, and order matters, which means if I grabbed a group of 3, I can actually arrange them multiple times before I need to go to another person. In fact, 2 of those people could stay, and I could throw a third guy in there and do that 3 different ways, right? And so, or more. And so you have order that then starts to come into play. So let's look at this first one, example 4. We have how many 4-letter arrangements can be made from A, B, C, D, E, F, G if letters cannot be repeated, all right? The fact that they cannot be repeated is important, and the fact that we are arranging letters is also important because I can pick A, B, C, and D, and it's telling me how can I arrange them. That's not just telling me to group them, all right? Arranging is indicating that I'm putting them in a specific order. And so I am going to do a permutation. My first number here is going to be how many I have. Well, I have 1, 2, 3, 4, 5, 6, 7. I have 7 objects. 4-letter arrangement. That tells me how many I'm taking at a time. And so I'm going to say, well, that is 7 factorial over 7 minus 4 factorial. By the way, this is when I would do something like this because 7 minus 4 is just 3 factorial. And so that's what that looks like, which is why we divide, by the way, when we do the other one. All right, or you can do 7 factorial divided by 3 factorial. It doesn't matter. Either way, you're going to get about 840 options here. So this is distinguishable. So distinguishable permutations. We have given n objects with a certain number. N of 1 is just a certain number of identical objects of one type. N 2 of identical objects of a second type. They're just saying that somewhere in your grouping you have a repeated object here. The number of distinguishable permutations is going to look like n factorial over the ones that you have that are repeated. All right, the ones that you have that are repeated. And so the examples they give us are butterfly and caterpillar. And so if we look at the word butterfly, we have something that is repeated. What is repeated in the word butterfly? T. And so they're asking how many ways can I arrange those letters? Well, the problem is that I could arrange those letters in my same old permutation way. All right, but if I want to distinguish it, then I have to distinguish between the T's. All right, so you're not going to be able to distinguish because those are identical. And so you're going to take the number of letters that you have, which is going to be what, 9? 1, 2, 3, 4, 5, 6, 7. Yep, 9 factorial. And you're going to put that over however many of repeated you have. You have T and you have 2 of them specifically. So I'm going to say, well, that's going to be 9 factorial over 2 factorial. All right. Look at the next one. Caterpillar. Altogether, I have 11 letters there. What about my repeats? All right, I have an A and an A. I have 2 of those, so that's 2 factorial. All right. And then I have what? Yep, I have 2 L's. One more. Yep, R. 2 R's. That's going to look like that. All right, you're just multiplying your repeats by how many times they... So the factorial number, you're literally just counting how many times it repeats. By the way, that's how many times you can arrange those letters. And that's about how many caterpillars are out right now. Combination is the collection of objects in which order is not important. The number of combinations of n objects taken R at a time is written C n of R. N being your total number, R being how many are taken at a time. You'll notice that you still have your count over your count minus how many you're taking, but then you also have something else in the denominator. Is this going to make this smaller or larger? So it should naturally be, yeah. Permutation should naturally create more options than combination. Why? Well, if I take 3 of you out of this class as a group, and order does not matter, all 3 of you count as just one group because order does not matter. However, if I throw in order, then I can arrange just those 3 multiple ways, and that increases the number of options I have. So permutations are naturally going to create more options than combinations, naturally, all right? Again, you can use your calculator. You can do your 8 factorial over your 3 factorial, 5 factorial. You're certainly welcome to do this. I do it this way, and then I do my little canceling here, right? So, I mean, you can do it however you want. Either way, you're going to get the same answer, right? Look at the second one. That's always going to be the same answer.
1.
Yeah, right. A combination. with the same two are always going to end up to be one. There's only one way you can take 12 people 12 at a time if order does not matter, right? And if order does matter, you're going to end up with just 12 factorial, by the way. So a committee of 2 women and 4 men will be selected from 10 students, of which 4 are women and 6 are men. How many different committees can be selected? So first of all, we have to figure out how many women are going to be selected and then how many men are going to be selected. And then we're going to apply the fundamental counting principles for those 2 options. All right. So we basically have an option for women and we have an option for men. All right. We have an option for women. We have an option for men. Okay. The thing is, those options are dependent on something. They're dependent on the grouping that we do from the smaller groups. So instead of just putting like if I just had 2 options and I just said there's this many, I'm going to do 1 of each, then I would say, well, the first option would be 4 women and the second option would be 6 men. And that would be my options, right? But now all of a sudden they're changing the dynamics and they're saying, no, I'm only taking 2 women. All right. And so out of my original 4. So that's actually a combination. 4 are how many women I have. 2 are how many I am taking for the committee. Make sense? So with my men then, I'm going to say, well, I have 6 altogether. I'm going to take 4. Make sense? And so all of a sudden my counting principle is based on then a combination, not just 6 times 4. Okay? So I'm actually doing it in a different way. So if I do these combinations individually, this is going to give me 6 options. This is going to give me 15 options. And so I end up with 90 different options when I do it that way. Okay. Fundamental counting principles. So in a multi-event process where there are possible outcomes for each individual event, whether they're dependent or independent, you can use your counting principle. Permutation. This is arranging certain objects in an order. Distinguishable means that you want to specify when you have repeated objects in a permutation. And then combination is you're just choosing groups out of total numbers where order is not going to affect it. All right. So arranging is going to be your key word here for permutations. Are you actually arranging them in an order or is it just grouping them? Are you just grouping the objects certain numbers at a time?